And just the last thing I wanted to mention, which hasn't really been talked about so far, is that we talked about electrochemical simulations. Peter mentioned this earlier, but one other kind of simulation that you can use with 3D data is you can take the data and port it into an actual 3D simulation of a structure development. In this case, something like nickel coarsening. And this is work that's been going on with Katsuya Thornton at the University of Michigan. They actually have a so-called phase field modeling capability. So they put in our initial 3D structure and then evolve it according to some rules. And this may be a movie of, so you can see the structure evolving here. Same color scheme, the green is the nickel, and the blue is the pore phase, and you can see that the nickel is moving around relative to the pore structure in this 3D microstructure. This is a full 3D simulation. So this is a summary of some of the results. So this is the percent TPB reduction as a function of time from their simulation. And I won't go into this in detail because I'm running out of time, but basically what they're doing is they're putting in different rules on the model as far as how diffusion occurs, what are the rates of diffusion, using different interfacial energies between nickel and YSZ. And you basically predict then different results as far as the way TPB reduction changes the temperature, or I'm sorry, the time. And some of this matches up reasonably well with the kind of numbers we're seeing experimentally, sort of in the 20 to 25% TPB reduction over 100 hours. So the idea is to eventually compare these with the experimental results and refine these models to get a better understanding of how the structure actually evolves. So I guess I'm probably out of time, so let me just leave the conclusions up here, and I'd be glad to entertain any questions.
Sharing some nice new data with us. We have about 4 minutes of questions if we don't want to eat up your lunch break. So, Ross.
Did you have a chance to check the pore size distribution and the close porosity with other techniques than this on your aged anodes?
No. But we did have 2 pieces of evidence. One was the actual pore epoxy infiltration, this kind of evidence, and then the FIB measurements. But what did you have in mind as far as other measurements? Did you have some idea of what other measurement we could do?
Measurements. Pressure process. On the same cells.
It may be a little difficult because we're looking actually at a very thin active layer. You may need more volume.
And since you saw there's such a huge difference, you might pick that up also.
My name is Lawrence Olsen from EMPA. We have now seen a lot of these nice 3D reconstructions and algorithms, and so my question is what information do you think could you get already from 2D, or asking in a different way, what kind of information is, where is 3D actually necessary in all your parameters that you are determining?
Oh yeah, well that's a very good point. And that we've kept asking ourselves that, because especially at the beginning, it was a lot of work to do with 3D. Why are we banging our heads against this wall all the time? But I think one thing that we're repeatedly seeing is that some of the key issues that are determining what's going on electrochemically are not accessible from 2D imaging. And those are particularly the connectivity of particles and tortuosity, which are things that I think would be very difficult, if not impossible, to get at from just 2D imaging. So that's the story we're seeing, is that the 3D, if you really want to understand what's going on in these things electrochemically, and I think also from the point of view of structural evolution, you'd have a very hard time doing that with only two-dimensional imaging.
Did you do any comparison for parameters from 2D and 3D, for example?
Yeah, James has done quite a bit of that, and so we did quite a few stereology measurements while we were struggling with segmenting these things, so we've got to do something else. But and the stereology, I mean, can do pretty good if you take enough surface area to get good statistics. It seems like it does very well with getting the volumes of materials and the surface areas start getting some error for the TPB density measurements. So those things you can get, I think, from stereology. But that, again, I think you're not going to get the connectivity.
Very quickly, how did you, the tortuosity measurements, geometrical or diffusion related tortuosity?
That was the same method that James mentioned. So we're actually taking the phase of interest and actually setting up a simulation where you put basically a gradient across it and observe the diffusion to the actual structure relative to basically a straight through structure. So there's actually an actual effective tortuosity that would be a correction to the diffusivity, conductivity of the structure.
So, what software did you use to do that? And did you struggle with the meshing to maintain the geometry of the?
That was done again by University of Michigan, Katsuya Thorne. And I don't think that's a meshing. That's a finite difference calculation. There's not meshing involved in that. If I'm remembering right.
It's a calculation of the voxelized structure on any differences.
Okay. But do you not have to coarse mesh the voxel structure to some extent to do that?
Like at areas where you have higher resolutions.
Because otherwise, you calculate transport across every voxel. Okay.
Yeah. It's actually somewhat time consuming. That simulation.
I think each calculation takes maybe a couple days.
Right.
So we've been, as James alluded to, we've been looking at alternative, easier, faster ways of looking at path lengths versus doing that full simulation, which often seem to work pretty well.
Okay. One quick last question.
Sheldon from the University of Lincoln. Regarding the comparison between the model prediction and the experiment for the polarization resistance, you still have quite a large difference, even if you consider the active three-phase boundary and also the tortuosity of the phases. So, do you have any idea for anything missing in the model, or how to make the two, more accurate?
Yeah, well, I mean, I often just fall back on saying we're a little bit surprised that it works as well as it does, considering the fact that we weren't using data from interfaces. We're just using averaged quantities from the 3D data set. And this Tanner von Bierkar model itself has some simplifications in it itself. It's just assuming basically straight through YSZ structure. That by itself could explain it, and that's perhaps motivation for going into a more complete real simulation of the electrochemical process. But James, did you have any other? We've talked a lot about why these things don't quite match up.
Yeah, and you can look at surface area relationships. In the case of the Ni-YSZ, you might actually have delamination from the electrolyte. But we'd love to do full electrochemical model. I think there's going to be some talks on that.
I think that's a good time to break for lunch now. I'd like to thank all the speakers again this morning.